A rocket is traveling at 0.8 c. How fast must it go to decrease its momentum by a factor of 4? Now, Einstein showed that the proper expression for momentum is actually gamma times mass times velocity. And this is the form that momentum must actually be if momentum is to be conserved in all situations. So that includes the very fast and, relatively speaking, the very slow. So very slow being our everyday speeds, very fast being something that's a significant factor of the speed of light. And of course, when you're talking about our regular ordinary speeds, gamma is essentially 1, and so this just becomes the more familiar form, P equals mv in that case. But we're looking at a situation here, a relativistic situation, so moving quite fast. And we want to figure out this situation. How fast does it have to go to decrease the momentum by a factor of 4? So the idea is this, here I'll use this expression, to be the initial momentum. And I got to put gamma initial because gamma depends on the speed. Now, I want it to decrease by a factor of 4. So that tells me that P final is P initial divided by 4. And I also know that P final is going to have to equal gamma final times M times V final. Okay, so I'm going to use this. I'm going to focus on just this part here. And I'm going to make my substitution for P initial. So just focusing on that, substituting for P initial, I have gamma initial, M, V initial. That's going to be divided by 4. That's going to equal gamma final, M, V final. Now, of course, at this point, hopefully it's rather straightforward to see that the masses cancel. We know V initial. We don't know gamma initial, but it depends on V initial. And again, we know V initial, so we can relatively quickly calculate the left side here. So let me put the values in. So V initial is 0.8 c divided by 4. And then I got to do 1 minus, this would be V squared over C squared. And of course, when I do that, well, let me write it out just to make it clear. 0.8 squared, C squared, over C squared, so the C squareds cancel. And I'm going to go ahead and write this side out like so. Okay, so I can quickly do the left side, like I say, get that calculated. So let me do that real quick. And I get, when I do all this, that this becomes C over 3. So C over 3, let me move that over here. C over 3 equals V final over the square root of 1 minus V squared over C squared. Okay, so now I got to solve for, and I left my V final, left my subscript off there. Okay, I'm solving for V final. That's what I need to get. And I've got this annoying square root. So what I'm going to do is, well, what the heck, I'm just going to cross multiply and I'm going to square. So I'm going to do both of those all in one step here. So let me divide my page. And then, like I said, cross multiply and square all in one step. So that's going to be C squared 1 minus V final squared over C squared. And that's going to equal 9 V final squared. Distribute the C. So I'm going to have C squared minus V final squared equals 9 V final squared. We're solving for V final, so this becomes C squared equals 10. When I bring that over, that's going to add, so it's going to be 10 V final squared. And then I'm going to have, so C squared divided by 10 is going to equal V final squared. Take the square root, and I'm going to have C over the square root of 10 is V final. And that's approximately 0.3162 c. And there you go. So to decrease the momentum by a factor of 4, the velocity would have to go from 0.8 c to 0.3162 c.